These are the notes on oxidation reduction part 3. So now we're going to look at oxidation on its own and reduction on its own. Even though they don't really happen on their own, there is a way of looking at them in what we call half reactions. So one way to show the oxidation or reduction portion of the redox reaction is by writing a half reaction that shows one of the changes. So here we see zinc producing zinc ions and electrons. Okay, electrons are shown as a product of this reaction. So if you think about this half of the reaction, what's happening? Zinc is losing electrons, zinc is being oxidized, right? That's the oxidation portion. But then those electrons have to go somewhere, so there's another half reaction for the other side. Notice that there are 2 electrons on the reactant side of this equation, things we don't usually show in a chemical equation. So you see 2 electrons plus 2 hydronium ions producing hydrogen and 2 water molecules. That is the other half of the reaction. Now, realistically, one of them can't happen without the other, but you can manipulate them with a barrier to cause those electrons to flow from one place to another. And that is the basis of batteries, which of course power many of our electronic devices. So by adding the 2 half reactions together, you get the overall redox reaction, the kind we've already talked about. Enough electrons are in each half reaction to keep the charges balanced. So if electrons go out on one side, they come in on the other. Free electrons do not actually leave the zinc atoms and float around before being picked up by the hydronium ions. They are basically handed off directly from one to the other in reality. So these are the rules for writing half reactions. You basically show either the oxidation portion or the reduction portion. Then you identify the reactants and products. You write an unbalanced equation in ionic form, and you can leave out any spectator ions that weren't really involved. For example, if you use hydrochloric acid, well, who cares about the chloride? What matters is the hydronium that is made. You can assign oxidation numbers. You can write and balance the half reactions. I will show an example of this in a moment. For each half reaction, you do the following. You balance all the atoms other than hydrogen and oxygen, just balance them automatically, put them on the other side. Then you balance oxygen atoms by adding water molecules as needed. Then you balance hydrogen atoms by adding any hydronium to the other side as needed. Then you balance the overall charges by adding electrons. To make the electrons equal and combine the half reactions, that's how you turn it into a redox reaction. So I know this is hard to understand, seeing the rules listed like this, so I'll show you an example. Here we have one of the products, zinc hydroxide. So we got to balance the zinc. Balance any atom other than hydrogen and oxygen. Then to balance the oxygen, I can add water molecules. Well, there's 2 oxygen there. Notice how that's a polyatomic ion. So I can put 2 water molecules there. Now I have to balance the hydrogen. Now notice we've got too much hydrogen on this side. We've got 4 atoms and only 2 on the other side. So we need to add some hydronium, okay? In order to make the oxygen balance, however, we have to change the water molecules now with a coefficient of 4. And then what's the last thing we need to do? Oh yeah, well the charges need to balance. So if you notice that there's a positive charge on hydronium and there's 2 hydronium, So in order to balance out two positives, what do we need? We need two negatives. So this gives us 1/2 of our redox reaction. Which half is it? Can you tell? Can you tell? It is the oxidation portion. So if those electrons are given off, well, they do need to go somewhere and complete the other half of the reaction. But in the meantime, you could use them to power an electrical flow. You could use them in a battery. So oxidation reduction is inherently confusing because we're dealing with negative particles moving. So when you're talking about reduction, remember, the oxidation number is going down, but what you're doing is you're actually gaining electrons. Okay? To simplify this, what they've done is they've defined electrical current the opposite way, not the way that electrons are actually going, but the way that a positive charge would be moving. So in a weird way, the way they've defined circuits and the way that electricity flows is the opposite of the way that the electrons actually move. Another thing that complicates oxidation reduction or redox is that a chemical that causes oxidation is called an oxidizing agent. However, the chemical itself often undergoes reduction. In the same light, reducing agents often are oxidized themselves. So again, if you're thinking about a chemical that is labeled as an oxidizer in the storeroom, it probably isn't going to get oxidized itself. It's probably going to be reduced. I know that's confusing as well. It will oxidize surrounding chemicals. So an oxidizing agent will accept electrons easily and be reduced. Common oxidizing agents are oxygen itself. Oh, that's why it's called oxidation. Hydrogen peroxide and all of the halogens, in the fluorine, chlorine, bromine, iodine family. Okay? Reducing agents cause reduction to happen. So then they themselves are oxidized. Examples of reducing agents are most metals, okay, other than the noble metals, hydrogen, and carbon. Got it? So when it comes to batteries, chemical batteries involve redox reactions. They have ends of the batteries that are called electrodes. There's an anode and a cathode. So what they do is they split up the reaction into its two parts, and they have the electrons carried from one end of the battery to the other in order to complete the reaction. The anode is the electrode where oxidation occurs. This is where cations may form. Now I know that's funny because it's the anode and cations are forming there. On the other end of the battery, you have the cathode. That is the electrode where reduction occurs. So this is where, guess what? Anions are forming. So again, once again, you kind of have to reverse yourself. When you're thinking about redox and you're thinking about batteries, we all know cations and anions from back when we learned about ionic compounds. But the place where the cation forms is ironically the anode, and the place where the anion forms is ironically the cathode, which also seems reversed. So in redox reactions, you have to reverse yourself and reverse yourself and reverse yourself. It can be very confusing, which is why we need these mnemonics like oil rig, okay? So at the cathode, where you are forming anions, okay, the reason you're forming anions there is because the electrons are attracted to the cathode. Opposites attract. Got it? And the anode, the reason you're forming cations there is because the electrons are departing from that end. They're leaving. Okay? Like charges repel. So electrons are repelled from the anode. So an electrode reaction describes reality because the electrons actually move from one electrode to another to continue the reaction. You really can't have just one part of the reaction without the other, but the connection they have is with the flowing electrons that can be used in the meantime to run an electrical current. Got it? So here is an example of two electrode reactions, two half reactions that can occur in an alkaline cell battery, and it can cause electrons to flow. Notice that in the top reaction, electrons are a reactant. So that is happening at the cathode. Why? Because electrons are attracted to the cathode, and they are arriving there, and they are participating as a reactant in that particular half reaction. At the anode on the bottom, the other end of the battery, usually the end that doesn't have a point sticking out, you see electrons are the product. They are produced by the reaction, and so they are given off by the anode. The anode is negatively charged, which repels the electrons along their way. So remember that in a battery, electrons flow from the anode to the cathode. Despite the way that we show on circuit diagrams, we show the electrical current the other way around. And that's just because moving negative particles is so confusing, they decided to just pretend it's a positive particle moving. Okay? So even if you see a circuit diagram that shows the opposite of this, this is the way that the electrons are actually flowing from the anode to the cathode. So man, there are so many things in redox that can be confusing. So many things where you have to flip yourself, reverse yourself. Ay, ay, ay. Okay? So hopefully you've got a small taste of it and how chemical reactions can be used to make batteries. So this is the end of Notes on Oxidation Reduction, Part 3. Bye-bye.